Hello, friends. How y'all doing? We are starting section 3.1 on invertibility and determinants. Let's get started. We'll start with some definitions. The first definition, that the n by n matrix, and since we're saying n by n, that means that the matrix is square. I sub n with columns that are the standard basis vectors. We call this the identity matrix. So I2 would be the matrix 1, 0, 0, 1. I3 is the matrix. Something just happened with my pen there. There we go. 1, 0, 0, 0, 1, 0, 0, 0, 1. In other words, these matrices are already in reduced echelon form. Making them really easy to work with. Sometimes we'll see an I without a letter, without a number, and this is just an identity matrix of unknown size. Okay? We're going to use this definition in the next definition. We're still working with square matrices. And we say a square matrix is said to be invertible if we can find another matrix B so that when we multiply them together using the column row rule, they cancel and give us an identity matrix. If so, the matrix B is called the inverse of A, and we write it as A inverse. So let's look at an example. Suppose that A is a matrix that rotates vectors clockwise by 90 degrees. And so A is going to take our standard vectors I and J, or E1 and E2, transform them 90 degrees clockwise. So the transformed version of E1 is now pointing down. The transformed version of E2 is now pointing to the right. And this is what the transition matrix, transformation given by A looks like. And so A is the matrix. E1 transforms to straight down, that's 0, -1. And E2 is straight across, that's 1, 0. And then B is the matrix that rotates vectors counterclockwise by 90 degrees. All right. So that takes I and J. Like say I and J, let's say E1 and E2. Transforms them counterclockwise, so the transformed version of E1 and the transformed version of E2. Go here, that's the transformation formed by matrix B. And so matrix B, E1 is now pointing straight up, and E2 is pointing to the left. And that's what B looks like. So construct A and B, we have done that. And then check that when we combine them, we get the identity matrix. That should happen if we rotate counterclockwise and then we rotate clockwise. That should get us our original position back. So let's try this. A times B is 0, 1, -1, 0 times 0, -1, +1, 0. All right. And divide this into columns, divide this into rows. So that's going to give us the first column, 0, -1, pairs up with the first row. When we multiply these together, 0 times 0 is 0, 0 times -1 is 0, -1 times 0 is 0, -1 times -1 is 1. And so there's our first part. Then we're going to take the second column and the second row, combine them. 1 times 1 is 1. 1 times 0 is 0. 0 times 1 is 0. 0 times 0 is 0. That's our second part. When we add them together, 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 0 is 0. And 1 plus 0 is 1. And that is, in fact, I2. So this works. So let's move on. Let's use the definition to find the inverse of this matrix. So by definition, then when I multiply by the inverse, let's call it A, B, C, D, the answer will be the identity matrix. Well, that tells me by the column row rule that when we take 3, 1 times AB, that gets us 3A, 3B, 1A, 1B. And then we're going to take -2, -1 times CD. That'll give us -2C, -2D, -1C, or -C and -D. When we add these together, we get 3A minus 2C, 3B minus 2D, A minus C, and B minus D. That should be a D there. All right. And so we get this system here. 3A minus 2C is equal to 1. A minus C is equal to 0. And then over here we have 3B minus 2D is equal to 0. And B minus D is equal to 1. And so we'll solve both of these systems here. From this system, we just have A is equal to C. And so 3A minus 2A is equal to 1. And so A is equal to 1 and C is equal to 1. 3 times 1 minus 2 times 1 is 1. 1 minus 1 is 0. So A and C are going to be 1. This one's a little harder to solve because B minus D is 1. And so B is equal to 1 plus D. We can make a substitution there. 3 times 1 plus D minus 2D is equal to 0. So 3 plus 3D minus 2D is equal to 0. So 3 plus D is equal to 0. So D is equal to 3. And B is equal to 1 plus D. So D is -3. Sorry, 3 plus D is 0. So D is -3. And so B is -2. And so by definition, the inverse is going to be A, which is 1, B, which is -2, C, which is 1, and D, which is -3. And that gives us the inverse directly using the definition, but later on today we'll see a shortcut for being able to do this without having to use the definition. All right? So this matrix is invertible. But we're going to show this using a different process here. What I want to observe from the last example is that these two systems of equations are structurally the same on the left side. The coefficients come from the original matrix A, 3, -2, 1, -1. And over here, even though the variables are different, the coefficients are still 3, -2, 1, -1. But the columns This is E1 and this is E2. And so what we're going to do is we're going to solve this system here by augmenting it with E1, but we're going to keep going. We're also going to augment it with E2, and we're going to augment it with E3 because we're going to know we're going to end up solving all three systems. And so we're just going to augment with all three columns. This gives us what we call a triply augmented matrix. But when we row reduce this matrix, let's go to the next slide. There we go. Then I'm not going to take the time to show you the row reduction. Once we put this into reduced echelon form, all of these pivots move to the left side of the bar. And then what we get on the right side is exactly the inverse of A inverse. And so I'm skipping the work here, but the idea is that we can invert this matrix by observing that we have systems of equations for all of the standard basis vectors that have the same left-hand side. And so if we work on all three systems at the same time, then we can solve them all together and get one inverse matrix for our answer. Okay? So this is a proposition in the book. It's 3.1.5. We can find the inverse of an n by n matrix by augmenting A with the identity matrix and reducing it so that the identity matrix is now on the left side and the right side is the inverse. In order for this to work, though, it means that A has to have n pivot positions. And so A has to have a pivot position in every row and every column. And that's going to come back to us later on when we combine the idea of being invertible with things like being independent and being a spanning set. Proposition 1.4 says that if we have an invertible matrix, then any equation of this form is consistent. And we know that because the other proposition says we have a leading entry in every row. That means there can't be a leading entry in the augmented column. And so the system has to be consistent. And the solution we'll find by multiplying both sides of the equation by b, and the b and the a will cancel because they're inverses of each other. And so we'll get x is equal to b times b. So this is summarizing what 3.1.4 says. If we have a system of equations, then x represents the coefficients in a linear combination with the vectors in A, and b represents the output vectors. That is, this is the input, and this is the output. But the inverse of a linear transformation switches the input and the output. And so if we switch the b and the x, then we should be getting the inverse of the transformation. And that's exactly what the end of 3.1.4 says, because A inverse is the vector matrix B. So B times capital B times little b, or A inverse times little b, gives us X. All right? So what we're going to do is we're going to use the previous example to solve this system of equations. See if we can make this work here. So in the previous example here, we did this row reduction. And we found the inverse of a matrix. Okay. See if we can make this happen. Nope, didn't work. All right. I'm just gonna copy this over. 1, 3, negative 2, 2, 3, 0, 3, 5, negative 1. 1, 3, negative 2, 3, 2, 0, 3, 5, negative 1. Let me double check that. 2, 3, 0. So let's see. That is the inverse of this matrix here. Negative 3, negative 7, 6, 2, 5, negative 4, 1, 4, negative 3. All right. So we found this by doing the row reduction as been done already. And so all we have to do now is just take this with these linear combinations. These are our weights. So we'll get 2 times the first column and negative 1 times the second column and negative 1 times the third column of the inverse matrix here using these numbers down here. And so in the top row, we get 2 minus 3 plus 2 is negative, it's positive 1, sorry. 2 plus 2 is 4, 4 minus 3 is 1. 4 minus 3 is 1, minus 0 is also 1. 6 minus 5 is 1. Negative 1 and negative 1 is plus 1, so that gives me a 2. And that should be the solution. We can check that. Negative 3 times 1 is negative 3. Negative 7 times 1 is negative 7. That's negative 10. 6 times 2 is 12. Negative 10 and 12 is 2. 2 plus 5 is 7. 4 times 2 is 8. 7 minus 8 is negative 1. 1 plus 4 is 5. 3 times 2 is 6. 5 minus 6 is negative 1, so that checks. So because the inverse encodes all of the row reduction that we've done before, then we don't have to redo the row reduction to solve a system of equations. If we know the inverse, we can then just work out that linear combination. I promise you a shortcut for 2 by 2 matrices, and here it is. If I have a matrix with 4 entries in here, a 2 by 2 matrix, then we're going to do 3 things. On the main diagonal, the A and the D are going to change places. So A goes down here and the D comes up here. So the A and D change places. On the other diagonal, the B and the C, they change signs. So B becomes negative B, C becomes negative C. And then the last thing we're going to do is we're going to multiply the whole thing by this fraction, 1 over AD minus BC. It's the 2 diagonals, the difference between them. So the main diagonal minus the other diagonal. And this works only if we are not dividing by 0. So let's try this on a couple of examples. Find the inverse of these two matrices. So the main diagonal switches places, but since they are both 2's, I can't see that anything's happened, but the 2's have switched places. The 5 and the -1 switch signs. And then we're going to multiply by the difference between the products of these columns. So 2 times 2 is 4. 5 times 1 is 5. 4 minus 5 is -1. So we're going to multiply by -1, and we'll end up with -2, 5, 1, -2. And that's the inverse. In the second example, the 3 and the 6 will switch places. The 2 and the 8 will switch signs. And then we have to figure out what we're going to divide by. So 3 times 6 is 18. 2 times 8 is 16. 18 minus 16 is 2. And so we'll multiply by 1/2. And so 1/2 times 6 is 3. Half of -2 is -1. Half of 8 is -4. And half of 3 is, well, it's 3/2. We'll get a fraction there. And that's the inverse of that matrix. Much faster than trying to do the row reduction for 2 by 2. This value, AD minus BC, is called the determinant of the matrix A. In the next section, we'll talk about what the determinant tells us about a matrix. And we'll also learn how to find the determinant for a matrix that's larger than 2 by 2. It's not quite as simple as what we just saw here, but it's still doable. All right? We have a couple of theorems to wrap up. Before we do this, one last definition. The rank of a matrix is just the same as the number of pivots in the matrix. So if I say that a matrix has rank 3, it means that the echelon form has 3 leading entries in it. Okay? If we start with a square matrix, then all of these statements are equivalent. If any of them are true, they're all true. So if a matrix is invertible, proposition 3.1.5 tells us that there is a leading entry in every column and every row. Because there is a leading entry in every column, then we have linearly independent columns. And because we have a leading entry in every row, the columns also are a spanning set for Rn. Since we have a leading entry in every row and they're in rows because it's a square matrix, the rank is equal to n. That uses our new definition. It's the number of leading entries. Every row has a leading entry, so there are n leading entries. The equation Ax equals 0 has only the trivial solution, and this is because if we look at the columns on the coefficient side, every column has a leading entry, and so none of the columns are free. Every column is basic. And since there's no freedom, we only have one solution, and it must be the trivial solution where we plug in 0 when we get 0. Also, every equation is consistent, even if the right side is not 0. And that's because we have a leading entry in every row on the coefficient side. Again, leading entry in every row. That means there's no row where the leading entry can be over on the augmented side. And so every single equation using A is consistent. And so knowing that a matrix is invertible automatically gives us a lot of these other facts. The columns are linearly independent. The columns are a spanning space. The equation Ax equals B is automatically consistent. Even if we haven't row reduced it yet to solve it, we know there's going to be a solution to it. Okay? All right. We have two other theorems I want to talk about. One is called the shoes and socks rule. Um, and the idea here is that if I want to find the inverse of a combination, this combination means something. It says that we're doing matrix B first, then we're doing matrix A, and then we're going to take the inverse of that. We can take the inverse, but the inverse turns out to be the reverse order. Um, and we call this a shoes and socks rule because of the idea that is in the morning, if the first thing I put on my feet is my socks, and then I put on my shoes, and then I want to undo that process, I have to take the shoes off before I take the socks off. That is, I have to take things off in the reverse order. You've seen this in regular um, calculus. If you have a function like, or an equation like square root of, say, natural log of x is equal to y, and you're trying to solve, you have to take, even though the ln happens before the square root, you have to take the square root. You have to take the outside function off first. Then you take the inverse function, inside function off, and you get e to the y squared. And so you have to take the functions off from outside to inside, and that's what we're doing the same thing here. So that's called the shoes and socks rule. The cancellation rule. In the past, we've mentioned that you cannot cancel matrices, but invertible matrices can be canceled. If I have AB equals AC, then I can cancel A by multiplying by the inverse of it. But they only cancel if they're on the same side. I can cancel the A's in AB and AC. But if one of the A's is on the left and one of them's on the right, then we still cannot cancel the A's. So we have some partial cancellation for invertible matrices. If they're both on the left, we can cancel them. And if they're both on the right, we can cancel them. But if one's on the left and one's on the right, we cannot cancel that. All right. Thank you for coming. We'll see you soon. Take care.